Hey guys, this video is going to be about VSEPR theory and molecular polarity. Alright, so VSEPR theory stands for valence shell electron pair repulsion theory, and it uses Coulombic repulsion, so Coulomb's law, between electrons as a basis for predicting the arrangement of electron pairs around a central atom. So before I go over the shapes and stuff, I want to show you something. So give me a minute, and I'm going to pull up a website, and you'll be able to see what I'm talking about here. All right, so this is a PhET, and I will post the links. They'll be at the end of this video. I'll also post them in Google Classroom. So I have an atom, and I'm going to just put two atoms bonded to it. So all I did was click on the two atoms, and you can see that this is linear. It's a straight line. If I add a lone pair to this, the lone pair of electrons would not be able to see anything if we were to take a, quote, picture of the molecule, but we do see that it has changed the shape of it because bonds are made from electrons, and so are the electrons, obviously, and electrons are all negative charges, and so they're going to move to balanced positions around that atom so that they can get as far apart from each other as possible. So right now, it would be kind of flat in shape if you look at it here, and so I'm just kind of moving it around, and it kind of wiggles and jiggles a little bit, but you can see that as I move this closer, it starts to move away, and so the bond angle here would be approximately 120 degrees, probably a little less than that, because it's going to be flat like a circle, and if a circle is divided into 120 degrees. Now these lone pairs of electrons, because they have such a big bubble there of space that it occupies, it's going to force those bonds a little bit closer together, and so the bond angle between those two, between these two things right here, would be a little bit less than 120 degrees, because this lone pair of electrons on the top will push those bonds a little closer. Now if I was to add another lone pair, it would push them even closer together, and so you can see how the shape would look, and you can play with it, okay? And if I was to add another bond, it would push them even closer together. Now if I take a lone pair away, so you can kind of play with it and look at the molecular geometry and the electron geometry and see what's happening. So I just wanted to show you that. And you can also look at bond angles. So it shows you the bond angles here and how they change when it moves around and all that stuff, okay? So that is going to be the PhET. So if we go back to the presentation, I have all the shapes here, and it says the electron pair geometry right here. All right, we have linear if there's two electron dense areas. You can also count the steric number. So the steric number is the number of positions electrons are organized around the central atom. I spelled that the British way, didn't I? Okay, when we have a steric number of 2, that molecule will always be linear. So something like carbon dioxide would have a steric number of 2 because the electrons are organized here and they're organized here. And so that would be a linear molecule. The bond angle here is always going to be 180 degrees because that's as far apart as they can get. Now, when we have a steric number of 3, we have some options. All right? So a steric number of 3, the electron pair geometry is trigonal planar. Now electron pair geometry is different from molecular geometry because we're looking at the electrons as well. So if I have SO3, or if I have SO2, we have either one of those molecules, they would both fall into the trigonal planar electron pair geometry because these electrons will affect these bonds. It won't be linear because those electrons are there in place, and so it can't adopt this shape because the electron pairs push those bonds down into the bent positions. All right, so we call it bent as a molecule because the molecules only take into consideration the atoms, whereas the electron pair geometry will take into consideration all of the electrons. So it represents the steric number. If you have 3 electron dense areas, or 3 is the steric number, you're going to have trigonal planar electron geometry, but you could have trigonal planar molecular geometry or bent. And so that's the difference between electron pair geometry and molecular geometry. You'll also see shape of the molecule, that's molecular geometry, molecular shape. All those mean the same thing. 4 would be tetrahedral, and tetrahedral can be, for the molecular geometry, it can be tetrahedral. So that's 4 and 0, 4 bonds, 0 lone pairs. 3 and 1, so that would be 3 bonds, 1 lone pair, or 2 and 2, 2 bonds, 2 lone pairs. All 4 of those, or all 3 of those, have 4 for the steric number because they have 4 electron dense areas around the central atom. When we talk about bond angles, we already said linear was 180 degrees, trigonal planar is 120, and tetrahedral is 109.5. Now, as we add the electron pairs, this would be slightly less than 120, and this one would be slightly less than 109.5. This one would be a little bit less, even more. Okay, and it only drops a couple of degrees, and I don't think that PhET shows this, but the electron pairs push these bonds a little bit closer together than they normally would be because they take up more space than a bond does. All right, now when we get past this at steric number 5, we get to trigonal bipyramidal electron pair geometry. And so this is basically 2 triangle pyramids, one on top and one on the bottom. And so this is 5 and 0. And then we have 4 and 1, 4 bonds, 1 lone pair. 3 and 1, or 3 and 2, 3 bonds, 2 lone pairs, and then 2 and 3. So you can see that this is a T shape. This comes out at you, so the wedges come out towards you. Sawhorse, or we called it seesaw, is what you might be more familiar with. And then we have octahedral. So octahedral has 6 electron pair geometry, and you can look at all those shapes there. We have square pyramid, square planar, T-shaped, and linear. So I'm going to work some examples and assign the electron and the molecular geometry to this. You might want to print one of these out. I will have one attached. I'll have this one attached, or write it down in a way that you can understand it. One thing that I forgot to mention, trigonal bipyramid. So the angle here is 90 degrees, and the angle here is 120. So those are the 2 bond angles there. And then in octahedral, everything is 90 degrees. But the ones that you really need to know are the tetrahedral and the trigonal planar ones. All right, so first we have ICl2. So iodine has 7 valence electrons, chlorine also has 7, and then we have 1 extra electron. So that's 22. So iodine is going to go in the middle. I'm going to bond in my chlorines. So I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, and 22. And I'm not going to make any double or triple bonds because I have plenty of electrons. It actually exceeds the octet rule, and so I'm going to check, can iodine do that? Yes, it can. It's below the 3rd period. And then I'm going to look at my central atom and say, okay, how many electron dense areas are there? And if I look and see, there are 1, 2, 3, 4, 5 electron dense areas around iodine. So that would be trigonal bipyramid. And since I have 3 lone pairs and 2 bonded atoms, this would actually be linear for the molecular geometry. And this is the electron geometry, because the electron geometry takes into consideration everything, while the molecular geometry is really only looking at the arrangement of the atoms. All right, and then we have BRF5. So this is 7, and this is 7 times 5. So that would be 42 electrons. So there is 10, 12, 14, 16, 36, 38, and 40. So I have 2 more electrons, so I'm going to put them on the central atom. Even though I've already exceeded the octet rule, that is fine for bromine. It's below the 3rd period. And if I look, I have 6 as my steric number, or there are 6 electron dense areas around bromine. There's one here, 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 here. That's 4, 5, and 6. So that would be an octahedral for the electron geometry because it takes into consideration everything. And then within the octahedral electron geometry, I have 5 bonds and 1 lone pair, which means that this would be a square pyramid. All right, now this one, all we have to do is fill in the electrons. So 24 valence electrons. Right now I have 2, 4, 6, 8, 10, 12, 14, 16 valence electrons out. So that means I need to put 8 more. So there's 2, 4, and then 6, 8. And in this one, we have all sorts of different things we can look at. So I'm just going to say, what about this carbon? Well, that carbon would have tetrahedral, electron geometry, and tetrahedral molecular geometry. Because it doesn't have any lone pairs, so its electron geometry and its molecular geometry would be the same. So the bond angles here would be 109.5. And then we have carbon, which is going to have 3 as a steric number. And so we have trigonal planar. That is going to be for both the electron and for the molecular because it doesn't have any lone pairs on that carbon. So we're just looking at carbon for that. All right, and then down here for the oxygen, oxygen has a steric number of 4. So the electron geometry is going to be tetrahedral and the molecular geometry would be bent because it's bent down. We wouldn't see these in a picture, quote unquote, a picture of the molecule. We would only see the atoms in place. So we can tell that those electrons are forcing those bonds down because the bonds get closer to one another than they normally would be. All right, so this is hydrogen peroxide, H2O2. So hydrogen has 2 valence electrons and then oxygen altogether would give 12, so that's 14. So right now I'm showing 6, so I still have 8 more to go. So that would be 2, 4, 6, 8 for that oxygen. And all the octet is good on that, so that's the structure. And that oxygen would have a electron geometry of tetrahedral and then a molecular geometry of bent. So if you look at your sheet that you have of all the molecular geometries, there is a steric number of 4 but 2 lone pairs, and so that would be bent formation. And so the bond angle here around that oxygen, the angle between the bonds around that oxygen would be a little less than 109.5 because of the lone pairs that are there, because tetrahedral geometries have a bond angle of 109.5. All right, so the reason that we care about VSEPR theory is to look and see if a molecule is polar or not. And if the electrons are not distributed evenly over a molecule, the molecule is polar. So we've talked about what polar bonds were when the electrons weren't shared between 2 atoms equally. But if overall the molecule is polar, then that means the electrons in the molecule are pulled to one side more than to the other side. And that can be caused by one side of the molecule containing electronegative elements while the other side doesn't. So I'm just going to draw these structures. So we have H2CO. And that's what the structure would look like. And then just for practice, this carbon has a steric number of 3, and so it's going to have a trigonal planar arrangement. And that's really important because it helps us see these things in 3 dimensions. And that takes a little bit of practice. But I know that oxygen is really electronegative because it's right next to fluorine. So that means that this bond between carbon and oxygen is pretty polar. The bond is. So the electrons in that bond are being pulled towards oxygen. And so it's going to be slightly negative on this end. That's a lowercase delta. And it'll be slightly positive on carbon's end. All right, and carbon and hydrogen have very similar electronegativities. Carbon is a little bit more electronegative, but we still consider bonds between carbon and hydrogen to be non-polar bonds. So overall, we have the electron density being pulled towards oxygen, and so this is the molecule's dipole. And so it would be a polar molecule towards oxygen. And then if we look at HCl, okay, this would be linear because it's just 2 atoms, it's a straight line, and chlorine is pulling electron density away from hydrogen, and so it would be polar in that direction. We can also look at lone pairs forcing the molecule to be polar. So if we look at O3, O3 doesn't look like it would be a polar molecule because it's all the same atom. But in reality, we do see quite a bit of dipole. And it's because the uneven distribution of electrons. So this oxygen down here on the bottom has a lot of electrons, and it would be in resonance with the other one, like that. And so because of all of this negative charge down here, the bottom would be slightly negative while the top is slightly positive. Water. A lot of people draw water like this, which is fine, but you need to realize that this is bent because those lone pairs of electrons push those bonds down at an angle. So this would be tetrahedral for the electron geometry, but it would be bent for the molecular geometry. And because of that, and all of the negative electrons that's up on oxygen, we can draw it like this, and you can see it much better, that the electrons in the bond between oxygen and hydrogen are being pulled up towards oxygen because of oxygen's electronegativity. So they're being pulled by oxygen, and so it's going to be slightly negative on oxygen's end and slightly positive on the hydrogen's end. And so that makes a polar molecule. And then we have NH3, okay, and ammonia, which is NH3, is going to be a tetrahedral electron geometry with a trigonal pyramid molecular geometry. Okay, and I want to look at ozone, O3, and ammonia, and then also the H2CO on a website so that you can see how it's polar. All right, so this is CH2O or H2CO, and you can see the molecule. We can spin it and move it around, but it's the same structure that I drew. You just can't see the valence electrons because you can't see electrons in a molecule. You can just see where the atoms are. And we can look at the bond dipoles, and so you can see here they've drawn these little bitty dipoles on the ends of the hydrogen, showing that there is a little bit of pull towards the carbon, but you can see the big line that's on the carbon to oxygen bond. And so those electrons in that bond are really being pulled towards the oxygen by oxygen's electronegativity. And if I look at the electrostatic potential map, we can see that the red part is where the negative part of the molecule would be, and the blue part is where the positive end of the molecule would be. So we can see that there's definitely more electron density around the oxygen and much less around the bottom half of the molecule, the left half of the molecule. And if I take that off, I can press something else here. I can press molecular dipole, and it will show me the dipole of the molecule. And it says that the dipole here is 2.1864 dBi. Now, dBi is the unit that we express a polar molecule in a dipole moment. And it can actually be calculated, which we're not going to do. But if it has something like 0, then it obviously doesn't have polarity. So if I were to look up here and just look up chlorine, the molecule, and then press molecular dipole, it has 0 dBi because this would be nonpolar because it would just be two chlorine atoms put together. All right, so now if I look up ozone, we get this bent, right? It's bent because it's not linear. It would have a lone pair up on that central oxygen. And the bond dipoles are a little bit towards the outside, the bottom oxygen, because they have so many lone pairs of electrons. You can't just say that it's going to be polar because of lone pair electrons only. If this was linear, it would be nonpolar because those two dipoles would cancel out because they're going to be equal to each other. But because it's bent, it does have a little bit of polarity. Now, it's obviously not as much as the one we just saw, but you can see that it is a little bit more polar. All right, but if it was linear, like CO2, where these bonds are polar, you can see that the bonds are polar. Those are the bond dipoles. But when we look at the molecular dipole, it's 0 because they cancel each other out because it's linear. There are no lone pairs on the carbon in the middle to make it be bent. And so those lone pairs in the middle of ozone on that middle oxygen cause it to be bent, and then it becomes unequal because of the lone pairs on the oxygen. So you have to really consider the shape. All right, and then we'll look up ammonia. And so here's ammonia, and the bond dipoles, like we expect, go toward nitrogen because nitrogen's very electronegative. I'm going to turn that off and look at the molecular dipole here. So all of the electron density is being pulled up towards nitrogen, and nitrogen has a lone pair that gets added to it. And so we can see up there on the very top is very, very negative, and then at the bottoms where the hydrogen is really, really positive because nitrogen is sucking away all of the electron density towards itself. And so that would create a partial negative charge on the nitrogen where all the electrons are being held, and then a partial positive charge on the hydrogens. All right, that is pretty much what I have to show you. I'm going to put both of those websites up so you can play with them and use them while you're doing your classwork for this. And so here they are. So this is the bottom one is the 360 model molecules. It's where you can look at the polarity and stuff. And then the PhET is where you can just mess with the molecular geometry and electron geometry and kind of click on those and look at the bond angles and stuff.